All right, here we go. Hard lining, hardness, while flaying you. Sure, continuing. 2.5.1.5.2.2. When the acrylic resin is in the dough stage, it's removed from the jar, kneaded lightly with gloved hands or between plastic sheets until uniform, formed, and placed into the mold. The resin is trial packed under pressure. The flask. Yep, pausing. Take your time. When you're ready, just tell me where you want to pick back up, and I will jump right back in. Got it. Jumping right to section 2.41. A great variety of materials have been used over the years to make denture bases. Today, a plastic material is by far the most universally used. The chemical name is methyl methacrylate. The common name is acrylic resin. Since it was first introduced in 1937, a considerable amount of refinement and improvement has been made in acrylic resin and in the methods of handling and processing it. Manufacturers supply acrylic resin as both a powder, called the polymer, and a liquid, called the monomer, or in the form of a pre-mixed gel. The powder in liquid form is the one most commonly used. When the material is supplied in this form, the technician adds a measured amount of powder to a specific volume of liquid to form a dough. The dough is then packed into the denture mold, and heat is used to cure or harden the denture. Dry heat can be used, but curing in hot water is the most commonly used method. Known as polymerization, the cure or hardening of the acrylic resin in the mold takes place by a chemical reaction between the powder and the liquid. The types of denture-based materials are shown in Table 2.5. Two point five point one point one point two. Packing the dough at the proper stage. When the acrylic resin is in the dough stage, it is removed from the jar, kneaded lightly with gloved hands or between plastic sheets until uniform, formed, and placed into the mold. The resin is trial packed under pressure, the flask is opened, any flash is removed, and the procedure is repeated until the flask closes completely without excessive flash. 2.5.1.5.3 Improper curing. Too short a curing cycle or too high a temperature causes the monomer to boil during polymerization, resulting in gas bubbles within the acrylic resin. 2.5.1.4.4 Lack of adequate pressure during processing. Insufficient pressure during the curing cycle does not compensate for the shrinkage that takes place, thereby causing porosity. 2.5.1.5.5 Non-uniform thickness of the denture base. If a denture base is bulky in some areas and thin in others, more heat is generated in the bulky area during polymerization. If the heat is sufficient to boil the monomer, porosity occurs. Table 2.5 Types of denture-based materials. Number 1. Heat-cured denture resins, powder plus liquid. Use. Complete and removable partial denture bases. Comment. Improper packing or processing results in contamination, breakage, porosity, and other defects. Heat is required for polymerization. Number 2. Heat-cured denture resins, gel. Use. Complete and removable partial denture bases. Comment. Basic composition is the same as the powder and liquid varieties. Must be refrigerated to inhibit polymerization. Number 3. Auto-polymerizing acrylic resins. Use. Repairs, relines, impression trays, and base plates. Comment. Heat is not required to induce polymerization. Can be applied by the sprinkle method or used in dough form. Number 4. Resins for tinting. Use. Tinting standard pink denture base material. Comment. Pigments may be mixed with the polymer powder or packed separately. Number 5. Tooth-colored resins. Use. Custom denture teeth, temporary fixed prostheses, repairs, and similar applications. Comment. Fine polymer powders available in a variety of natural tooth shades, supplied in self-curing and heat-curing forms. Number 6. Soft lining resins. Use. Tissue conditioning denture liners. Comment. Polymerized to a semi-soft state. Number 7. Vinyl resins and polystyrenes. Use complete and removable partial denture bases. Comment: special processing equipment is required. Section 2.42 Heat-cured, heat-activated denture resins. Heat-cured denture resins are processed in the dental laboratory using heat and pressure to obtain a product that meets the requirements of the particular appliance being constructed. Heat-cured denture resins are supplied as a powder, the polymer, and the liquid, the monomer. The monomer has an inhibitor to prevent polymerization until activated by heat. Monomer is highly flammable, is a skin and eye irritant, and is known to cause allergic reactions. Two point four three, acrylic resin gel. This is a pre-mixed form of acrylic resin. The manufacturer mixes the powder and liquid at the factory and adds an inhibitor that prevents polymerization until the resin is placed in the mold and heated. The gel is more homogeneous because it is machine mixed in large quantities. It is somewhat handier and quicker to use, but its shelf life is limited, so it must be refrigerated when stored. 2.44 Autopolymerizing, chemically activated resins. Composition. Another member of the acrylic resin group used in the dental laboratory is the auto-curing or self-curing resin. The basic composition of these autopolymerizing resins is the same as that of heat-cured denture acrylic. The difference is that instead of using heat to bring about polymerization, a chemical activator is added to the liquid so the dough polymerizes in about 10 to 20 minutes at room temperature. Uses. Self-curing acrylic resins are used for most denture repairs. In repair procedures, they have a decided advantage over heat-cured resins because the denture does not have to be subjected to a high curing temperature that can often cause the denture base to warp. These resins are also used for impression trays, record bases, and denture base construction. The self-curing resins can be mixed and used as a dough, or they can be applied by the sprinkle method. The liquid provided with self-curing resins should always be thoroughly shaken before use because the activators are lighter than the liquid and tend to rise to the top of the bottle. 2.45 Acrylic resins used for tinting. Methyl methacrylate resins are used to modify the color of basic pink denture-based plastics. The pigments are used to more closely simulate the colors of natural gum tissue in the finished denture base. Some are applied to the desired areas of the denture mold before the resin material is packed. Some are shaped into preformed patterns that are placed in the mold prior to packing. 2.46 Hard lining resin. This is a slightly different type of acrylic resin which is marketed and intended for one-step clinical denture relines. The material has been compounded specifically for clinical purposes and does not lend itself well to laboratory use. It can be used for impression trays if a more suitable material is not available in the laboratory. 2.47 Tooth-colored acrylic resin. Tooth-colored methyl methacrylate resins are very similar to denture resin except for the color and finer particle size. Tooth-colored pigments are added to the polymer to simulate natural tooth shades. Tooth-colored acrylic resins are available in heat-curing and auto-polymerizing forms. They can be used to make denture teeth, veneer crowns, temporary restorations, and for repairs. 2. Let me look at that and pick up smoothly from section chapter 2.48. Sure. Starting at 2.48. 2.48 Soft lining resins. Some clinical conditions require a soft, cushion-like liner on the tissue side of denture base. These soft materials are usually known as resilient liners. It is important for these lining materials to bond well to the denture base, resist tearing, and retain their cushioning effect. There are three basic kinds of lining resins: vellum acrylic, silicone, and ethyl methacrylate. 2.481 Vellum acrylic resin. Vellum resin is a form of acrylic resin that never polymerizes rigidly like ordinary resin. It is supplied as a powder and a liquid. The liquid is much more viscous than regular acrylic liquid and contains a retarder that prevents the resin from hardening. The principal use of vellum resin is in cleft palate prostheses. It is occasionally used as a denture reliner when a soft material is needed. Unfortunately, the ingredient that keeps the resin soft is eventually lost. As that ingredient is lost, the liner gradually hardens. Once that happens, it must be replaced. 2.482 Silicone resin liners. These soft liner materials, composed primarily of silicone gum and liquid or paste hardener, are available as either heat cured or auto polymerizing types. Silicone liners are the most truly elastic of the soft lining materials. However, they have a major disadvantage. They have poor abrasion resistance and are difficult to trim properly. Also, like vellum resins, silicone liners do not remain soft indefinitely, although they harden more slowly than other lining materials. 2.483 Ethyl methacrylate, such as Softpak and Durasoft. Ethyl methacrylate is a two-component, heat-processed resilient material designed for long-term denture relines and maxillofacial prostheses. Ethyl methacrylate bonds to methyl methacrylate, increasing its durability in the mouth. It's processed using standard techniques. The liner can be used against fresh acrylic during the initial processing of a new denture, or it can be cured against an existing denture base. Ethyl methacrylate offers easy polishing and finishing. It can easily be trimmed with a carbide burr or arbor band. It's then polished to a luster using a cloth wheel, pumice, and polishing compound. 2.49 Tissue conditioners. Until the patient's oral tissues return to a healthy state, the dentist may use tissue conditioners as a temporary soft liner for dentures that require relining. Tissue conditioners should be changed at 3 to 4 day intervals. Some clinical techniques use tissue conditioning resins in a denture base as the master impression for relining or rebasing an old denture, or fabricating a new one. Because these materials are very delicate and do not adhere well to the denture base, tissue conditioner impressions must be handled with great care in the laboratory. 2.50 Vinyl resins and polystyrenes. Vinyl and polystyrene are plastics which are chemically similar to acrylic resin, but differ somewhat in their physical properties. They are formed into a denture using a molding method known as injection molding. Advocates of these materials say they have superior dimensional stability compared with acrylic resin dentures. 2.51 Handling acrylic resin. Acrylic resin, with all its good qualities of excellent appearance, ample strength, lightweight, and ease of cleaning, it's far from foolproof in its manipulation. Even when properly handled throughout the processing procedure, acrylic resin is subject to dimensional changes. These changes appear as minor faults in the occlusion and loss of contact with the master cast. The changes are more noticeable across the posterior palatal seal area of a maxillary denture. However, these changes can be kept to a minimum when the technician understands the behavior and working characteristics of the material and takes precautionary steps to avoid certain pitfalls. The errors that are most likely to occur are distortion, contamination, warpage, breakage, and porosity. 2.511 Wax distortion. Distortion can be introduced during the wax-up stage that may alter the occlusion on the finished dentures. To minimize these effects of baseplate wax up one denture at a time. After the wax-up of the single unit is completed, it should be returned to the articulator and the occlusion examined. Correct any discrepancies in the occlusion before removing the other cast for wax-up. After completing the wax-up of both upper and lower dentures, examine the occlusion and correct any changes before beginning flasking procedures. 2.512 Acrylic resin contamination. Acrylic resin is especially susceptible to contamination while it's being mixed and packed in the mold. Meticulous cleanliness must be practiced, and clean measuring containers are essential. The mixing should be done in a clean jar with a stainless steel spatula. Hands should be gloved and kept very clean. Acrylic resin liquid is an excellent solvent, capable of dissolving grease and dirt from hands. A standard precaution is to handle the resin dough with plastic gloves or sheets rather than with bare hands. The mold must be absolutely clean and dry before the resin is packed. 2.513 Acrylic resin warpage. During the curing phase, several dimensional changes occur in the acrylic resin. The net effect is shrinkage. A characteristic of acrylic resin is that it shrinks toward its greatest bulk. In a denture, this bulk is in the area over the alveolar ridge. From wax up to finishing, this distortion can be kept within acceptable limits if each step in processing is carefully controlled. 2.514 Resin breakage. Most breakage of acrylic resin occurs during the recovery of the denture from the mold. The breakage is often the result of careless deflasking. Deflasking cannot be hurried, so take the time to do it properly. 2.515 Porosity. Porosity may be due to an improper liquid to powder ratio. The ratio of powder to liquid is important when mixing acrylic resin. A high percentage of powder speeds up the set and tends to reduce shrinkage during the cure. However, enough liquid must be used to thoroughly wet the powder so the chemical reaction can be completed. The usual ratio is 3 parts powder to 1 part liquid by volume. 10 cubic centimeters of liquid to 30 cubic centimeters of powder is generally considered adequate for the average denture. Measure the liquid first and pour it into a clean jar. Then measure and sift enough powder to absorb all the liquid. Tap the jar on the benchtop to bring any excess liquid to the surface, and then add the remaining powder. Stir the powder and liquid thoroughly with a stainless instrument. If it isn't well stirred, the color in some brands of acrylic tends to float to the surface. Then place a lid on the mixing jar and allow the resin to sit for several minutes. Then remove the lid and test the mix by placing the blade of a spatula between the mix and the side of the mixing jar. When the mix no longer sticks to the side of the jar, most heat curing resins are ready to pack. First, it appears sandy, then stringy, and finally doughy. So when it reaches the doughy stage, it's ready for the mold. One sec. Sure. Picking up from the end of 2.51522, when the acrylic resin is in the dough stage, it's removed from the mixing jar, kneaded lightly with gloved hands or between plastic sheets until it's uniform, formed and placed into the mold. The resin is trial packed under pressure. The flask is opened, any excess flash is removed, and the procedure is repeated until the flask closes completely without excessive flash. 2.5153 Improper curing. A curing cycle that is too short or at a temperature that's too high can cause the monomer to boil during polymerization. That produces gas bubbles within the acrylic resin, resulting in porosity. 2.5154 Lack of adequate pressure during processing. Insufficient pressure during the curing cycle fails to compensate for shrinkage that takes place. That causes porosity in the final denture base. 2.5155 Non-uniform thickness of the denture base. If the denture base is bulky in some areas and thin in others, more heat is generated in the bulky sections during polymerization. If enough heat builds up to boil the monomer, porosity develops in those thicker areas. And that concludes the common processing errors like distortion, contamination, warpage, breakage, and porosity. If your manual continues into the next section, happy to go on from there. picking up with section 2.542, ductility. Ductility is the property of a metal that lets it be drawn into a thin wire without breaking. A study of the tables of hardness and ducting. You're right, that's the end of what I have. If you share the next page, starting after figure 2.2, I'll continue reading from there. One sec. Sure. Starting again from section 2.521. Introduction. Metals are alike in certain aspects. There isn't an all-inclusive definition for metal that is entirely satisfactory. However, metals do have certain properties that distinguish them from non-metals. They possess a metallic luster, are good conductors of heat and electricity, and with the exception of mercury and one other rare metal, are solids at ordinary temperatures. Compared to non-metals, some metals are malleable, meaning they can be pounded or rolled into sheets. Others are ductile, meaning they can be drawn into wire. And most of them have a fairly high specific gravity, which means they're dense and heavy as a result. Metals also differ from one another in important ways. Each metal possesses physical properties that are unique to it. It has a fixed melting point, a definite specific gravity, and a certain degree of hardness, malleability, ductility, and so on. By knowing these physical properties, we can predict with a fair degree how a metal will behave under different conditions. In the same way, you can also predict the suitability of a as a dental restoration or structural prosthesis part. Okay, 253, structure of metals. 253.1, general properties. Metals are crystalline in structure, and many of their physical properties depend greatly on grain size and arrangement. Grains are essentially crystal clusters that form as molten metal cools and solidifies. Faster cooling generally produces smaller grains, and slower cooling produces larger grains. In general, smaller grains arranged evenly tend to give the most desirable properties. And the size and the arrangement can be changed a lot by how the metal is handled in the lab. That includes how much heat it's exposed to, how it's heated, how fast it's cooled, and how it's worked, bent, swaged, that sort of thing. Sure. One sec. Continuing section 2.53. Cast metal is a piece formed by pouring molten metal into a mold and letting it cool. And when rolling, pounding, or bending changes a casting's shape, that becomes wrought metal. Working the metal at room temperature changes its grain structure and can significantly affect its properties. With alloys, keep in mind that the combined behavior can't be perfectly predicted just from the individual metals. And you definitely want to choose dental alloys.
No.
Oh, sorry. What would you like me to continue? Sure. Starting from there. The physical properties of an alloy can't be precisely predicted just from the individual metals. For example, two metals of extreme hardness, when combined, might produce an alloy of only moderate hardness, rather than something as hard as either original metal. With few exceptions, the metals used in dentistry are alloys. You should understand the structure and physical properties of dental alloys. That knowledge lets you determine what combination of properties you need when choosing an alloy for a prosthesis and how to handle heat properly during manipulation so you preserve the desired properties. For physical properties, terms are precise, so it's important to know what they mean so you understand how the metal will behave. Suitability for a specific dental application depends on understanding those qualities. Hardness measures a metal's resistance to indentation or scratching. It's an indication of strength and wear resistance. For example, an onlay casting that takes heavy biting forces should be harder than a casting made for the facial surface of a tooth, since the forces are different. But metal can be too hard. Burnishing, which is the ability to adapt an inlay or crown closely to a tooth, depends on the metal's hardness. Harder metals are more difficult to burnish. One sec. Sure. Continuing from section 2.54.1.3. Several methods are used to measure hardness. When an alloy has been tested, it gets an index number. Depending on the test, you might hear Brinell, Vickers, or Rockwell hardness. Higher numbers mean harder metal. Brinell hardness is determined by pressing a steel ball into a dental gold alloy with a measured load and measuring the indentation. The Vickers test uses a diamond-shaped pyramid and works well for a broad range of materials and is commonly used for dental gold alloys. Rockwell hardness is another standard measure, common for chromium alloys. Ductility is the property that lets a metal be drawn into a thin wire without breaking. Generally, as hardness goes up, ductility goes down. And that relative ductility for several metals is listed in figure 2.2. All right, continuing. Great, great. One sec. Sure. Picking up from 2.54.11.1. When an alloy gets hot enough, it first softens and mushy. As heat increases, it becomes more fluid until it behaves like a thick liquid. The temperature where it just begins to melt is the solidus temperature. The point where it becomes completely liquid is the liquidus temperature. The interval between those two is the melting range. Knowing that range matters because overheating can damage the alloy and alter its physical properties. Metals also conduct heat pretty well, which matters in dentistry because restorations made from highly conductive metals can transfer temperature changes quickly to the tooth underneath. That wraps up the main physical properties of metals. Next, heat treatment. One sec. Sure. Starting section 2.55, heat treatment of metals. Heat treatment is the controlled heating and cooling of a metal or alloy to get the desired properties. There are a few key methods. Annealing, which heats and then lets the metal cool in a controlled way to relieve stress and restore ductility. Hardening, used to increase hardness and strength for better wear resistance and stress relief. which removes internal stresses from bending or grinding. Got it. Checking that. You're right. Let's go back to section 2.54.3. Malleability is the amount of extension a metal can take in all directions without breaking from hammering, rolling, or burnishing. That's what makes it possible to burnish the margin of a gold restoration closely to the tooth and reduce leakage. Gold is the most malleable metal. 1 grain can be rolled into a leaf covering about 6 square feet. More brittle metals are less malleable. Specific gravity compares the weight of a metal to the same volume of water. Water is 1 as the standard. So a metal with a specific gravity of 2 weighs twice as much as the same volume of water. See table 2.6 for specific gravities of metals. Elasticity, flexibility, and resiliency all refer to an alloy's ability to bend under pressure and then return to shape. This is especially important for RPD clasps, so they can flex over the contour of a tooth without putting harmful pressure on tissues. Elastic limit, proportional limit, and yield strength are terms that all describe the maximum stress a metal can take without permanent deformation for practical purposes. One sec. Sure. Picking up from section 2.54.7. Percentage elongation measures how much an alloy can deform without breaking. It should be as high as possible while still meeting strength needs. Grain size depends on cooling rate. Slow cooling makes larger grains. Rapid cooling produces a fine grain structure that's stronger. Grain growth happens when metal is heated for too long below its melting point, making it brittle. Malleability and ductility can sometimes be restored by proper heat treatment, but it's better to handle the metal so it never becomes brittle in the first place. When heated, gold alloys change color in predictable ways, which lets you roughly gauge temperature by color as described in Howe's color scale. For example, dull red is about 1,020 to 1,150 degrees Fahrenheit. Cherry red is around 1,300. Light red about 1,560. Orange around 1,650. Yellow roughly 1,740 to 1,920. And white is 2,100 degrees Fahrenheit or above. Those are just approximate since color perception varies and the lighting matters. A metal may look black in bright sunlight, but appear red in the shade. For the best estimate, check the color under lighting that's as normal as possible. Melting range matters because overheating can damage the alloy and change its properties. Metals are generally good conductors of heat, which matters in dentistry because restorations made from highly conductive metals can quickly transfer temperature changes to the tooth underneath. That completes the discussion of the main physical properties of metals. Heat treatment is the controlled heating and cooling of a metal or alloy to get the properties you want. If you have the next page of the manual, I can continue reading from there exactly as written. I'll review the attachments and summarize them for you. This page continues from section 2.54.11.2 through sections 2.55 and 2.56, ending at the start of 2.57. Melting red. Okay, checking that. Sorry about that. Continuing with the reading, section 2.57, effect of constituent metals. Aluminum is added to lower the melting range. It also Let me take a look. Sure. Starting over at 2.54.11, word for word. 2.54.11 melting range. 2.54.11.1. Pure metals melt suddenly at definite places or points on a temperature scale. Dental alloys do not melt abruptly at precise temperatures because they contain a number of metals with different melting points. When a high enough temperature is reached, an alloy first softens and becomes mush. As the heat is increased, the alloy gradually becomes more fluid until it finally behaves much like a thick liquid. 2.54.11.2. This gradual softening takes place over a spread of temperature known as the melting range. The lower limit of this range, known as the solidus, is the temperature at which the metal first begins to soften. The higher limit, called the liquidus, is the temperature at which the metal is completely molten. The spread of the melting range for most dental gold casting alloys varies from 75 to 150 degrees Fahrenheit. 2.54.12 Fusion temperature. The manufacturer does not provide the melting range of a casting alloy. Very often, the fusion temperature is provided instead. The fusion temperature is slightly above the lower limit of the melting range. It should never be exceeded when a metal is being soldered. The fusion temperature is provided to aid in selecting solder that has a melting range safely below the fusion temperature of the parent metal. This minimizes the possibility of overheating the parent metal during a soldering operation. I'm checking. All right, picking back up from 2.55 deformation of metal. 2.55.1. When an external force or load is applied to a metal, it is opposed and resisted by the internal force of the material's otherwise regularly spaced atoms, called stress. If the load is great enough, a change results in the distance between the atoms in the areas where the load is applied, called strain, and a degree of distortion or deformation occurs, which is directly related to the amount of the load and the direction in which it is applied. 2.55.2. A distortion that disappears when the load is removed is called an elastic deformation. When the stresses are removed, the atoms return to their original position. A distortion that does not disappear when the load is removed is called a permanent deformation. The metal is said to have exceeded its elastic limit, proportional limit, or yield strength. The stresses are not relieved, and the affected groups of atoms slip along a plane to new positions within the boundaries of their particular grains. 2.553. If a piece of metal is flattened by pounding or rolling, the individual grains are also flattened. As a pulling force is exerted on the metal, like drawing it through a die plate to form a wire, each grain is elongated to assume a fiber-like appearance. 2.56. Strain hardening of metal. 2.56.1 Strain hardening or cold working. When a metal is permanently deformed repeatedly, the metal becomes stiffer and harder. This process is called strain hardening or cold working. Continued application of a deforming load results in more and more atoms or grains slipping within the metal until the metal fractures. This is what happens when a paperclip is bent back and forth. Up to a point, it becomes stiffer and harder, then it breaks. 2.56.2 Annealing or heat treatment. 2.56.2.1 Annealing is the process of heat treating a metal to remove the stresses introduced by cold working and to prevent the metal's fracture. For example, there is a considerable amount of cold working to bend or contour a wire to form a clasp to fit on the surface of a tooth. 2.56.2.2 The strain hardness built up in a metal can be removed and the original properties restored by heating it to the proper temperature, for example, cherry red, and then cooling it rapidly by quenching in cold water. The cold working can then proceed because the regular arrangement of the slipped atoms has been restored and the stresses and strains have been relieved. The grains retain the changed shape caused by the cold working. Thus, ductility and malleability increase, but all other physical properties decrease. The metal is in its softest state, so a crown or inlay is most burnishable and a partial denture clasp is most adjustable. One moment. Sure, continuing. 2.57 Effect of constituent metals. The exact role of a metal varies with the particular alloy system the metal is added to. For example, copper is included in many of the high palladium alloys to help form an oxide layer for porcelain bonding. However, copper is added to the medium silver palladium alloys to effectively lower their melting range and permit the use of gypsum bonded investments. The following elements are frequently used in the traditional gold-based alloys. Note, their descriptions are generalized. 2.57.1 Aluminum Al. Aluminum is added to lower the melting range of the alloy. It is also a hardening agent and influences oxide formation. 2.57.2 Beryllium, Be. Like aluminum, beryllium lowers the melting range, improves castability, serves as a hardener, and influences oxide formation. Reportedly, it improves polishability by acting as a lubricant for polishing agents, thus permitting them to work more effectively. Electrolytic etching of nickel chromium beryllium alloys removes a nickel beryllium phase to create micro retention for the etched metal resin bonded retainers, also known as Maryland bridges. 2.57.3 Boron B. Boron is a deoxidizer, hardening agent, and element that reduces the surface tension of an alloy and thereby improves castability. In the nickel chromium alloys, boron acts to reduce ductility and to increase hardness. 2.57.4 Chromium Cr. Chromium acts as a solid solution hardening agent and ensures corrosion resistance by its passivating nature. 2.57.5 Cobalt Co. Cobalt-based alloys are an alternative to the nickel-based types, but are more difficult to cast. 2.57.6 Copper Cu. Copper serves as a hardening and strengthening agent, lowers the melting range, and interacts with platinum, palladium, and silver if present to provide a heat treating capability. It helps form oxides for porcelain bonding, lowers the density slightly, and can also enhance passivity. 2.57.7 Gold Au. Gold provides a high level of resistance to corrosion and tarnish with no associated passivity, and slightly increases the melting range as well as workability and burnishability. Gold imparts an aesthetically pleasing color to the alloy while markedly increasing density. Scanning. Sure, continuing from 2.57.8. Indium in. Indium serves as less volatile scavenging agent, tends to lower the melting range in gold-based alloys, helps form an oxide layer for ceramic alloys, and lowers the density. Reportedly, an indium content of 20% can adversely affect corrosion resistance of silver-based alloys. 2.57.9 Iridium IR and ruthenium Ru. These two elements serve as grain refiners to improve the mechanical properties and tarnish resistance. 2.57.10 Iron Fe. Iron is usually added to gold-based ceramic alloys to harden the alloy and aid in the production of oxides for porcelain bonding. 2.57.11 Manganese, Mn. Like silicon, manganese acts as an oxide scavenger to prevent the oxidation of other elements when the alloy is melted. It is also a hardening agent. 2.57.12 Molybdenum, Mo. Molybdenum is added to adjust the coefficient of thermal expansion and improve corrosion resistance. It also influences the oxides produced for porcelain bonding. 2.57.13 Nickel, Ni. Nickel has been selected as the base for alloys because its coefficient of thermal expansion is close to that of gold, and because it possesses a resistance to corrosion. It is easier to cast than the cobalt-based alloys. 2.57.14 Palladium, Pd. Palladium is added to increase the strength, hardness with copper, corrosion, and tarnish resistance of an alloy.
It increases the melting range and improves the sag resistance of a ceramic alloy. Palladium has a strong whitening effect, which renders metals as white alloys. It has a high affinity for hydrogen, and it lowers density of the alloy slightly. 2.57.15 Platinum, PT. Platinum increases the strength, melting range, and hardness while it improves the corrosion, tarnish, and sag resistance of an alloy. It whitens the alloy and increases its density. 2.57.16 Silicon, Si. Silicon serves as an oxide scavenger to prevent the oxidation of other elements during the melt. It is also a hardening agent. 2.57.17 Silver, Ag. Silver imparts a moderate increase in the strength and hardness of an alloy, with copper tends to tarnish in the presence of sulfur, possesses a rather high affinity for oxygen absorption, and lowers the density of the alloy. In ceramic alloys, silver lowers the melting range by counteracting the influence of palladium. Ceramic alloys with a high silver content may produce discoloration, green or brown, in many porcelains. 2.57.18 Tin, Sn. Tin serves as a hardening agent, tends to decrease the melting range of the alloy, and helps produce an oxide layer in ceramic systems. One moment. Sure. Continuing with the last bit of that section. Titanium, Ti. Titanium is added to lower the melting range and improve castability. It also acts as a hardener and influences oxide formation. Zinc, Zn. Zinc helps lower the melting range and acts as a deoxidizer or scavenger to combine with any oxides present. It improves the castability of an alloy and, when combined with palladium, contributes to its hardness. Zinc is commonly included in gold alloy solders. 2.58 Classification System. 2.58.1 The ADA classifies alloys according to the percentage of noble metals present. Noble metals include gold and the six members of the platinum palladium group: ruthenium, rhodium, palladium, osmium, iridium, and platinum. The ADA classification system is identified in Table 2.9. The next section on your page starts with 2.59.